Hi everyone. In this lesson we're going to be talking about supernovae. So we're going to learn first the difference between type 1 and type 2 supernovae. We're going to talk about specifically type 1 supernovae and how they're used as standard candles, similar to Cepheid variables in a way. We're going to get into the specifics of the processes that occur within type 1 and type 2 supernovae. And finally, we're going to talk about how to distinguish between these two supernovae. So let's get right into it. So first, what is a supernova? Let's get into the specifics here. So these are rare events in the universe. However, there are so many galaxies and so many stars in the universe that they're still observed pretty commonly. And they appear as extremely bright stars, where once there wasn't much of anything in that area of the sky. So we can kind of see that here. So in March 2011 versus September 2011, we can see there's a point in the night sky that just kind of appears, and that is supernova 2011 FE. Okay, so again, we get these bright stars that appear where there wasn't much there to begin with, and we can identify those as supernovae. And they're classified based on their absorption spectra into type 1 and type 2 supernovae. So first, let's talk about our type 1 supernova. So the difference between a type 1 and type 2 specifically is that the type 1 supernova absorption spectrum includes a hydrogen line, in addition to other lines as well. And type 1a supernovae are the ones we're going to focus on in this class. 1a, 1b, and 1c are all differentiated by other elements in their absorption spectra. But we're going to focus on type 1a because they're often used as standard candles. Now, type 1a supernovae occur in binary star systems, so kind of like to the diagram you see on the left-hand side there, we have two stars orbiting each other. And one of these stars in the system is a white dwarf, and because it's a white dwarf, it is extremely dense and has a very strong gravitational pull, so it starts to accrue matter from its sister star, the star it orbits. And this other star could be another white dwarf, or it could be a giant star as well. And it starts to accrue this matter. It builds up more and more matter, and eventually the mass reaches the Chandrasekhar limit. It collapses and then goes supernova. And this collapse creates extremely high radiation pressure. And this extremely high radiation pressure then blasts the matter of the star out into space. And it has a luminosity of 10 to the 10 times greater than the sun. And to use as a standard candle, we can use the apparent brightness of this supernova. We already know the luminosity because it's a white dwarf, and we know the Chandrasekhar limit. We can use that to find the luminosity. And if we know the luminosity and the brightness from Earth, we can use that to find the distance up to 1,000 megaparsecs. So a bit further than what we did with Cepheid variables. So it's a very useful phenomenon for us as astronomers. So with a type 2 supernova, we're going to start with a much more massive star than a white dwarf. And this is a star with 8 to 10 solar masses. And we know also when we have these very large mass stars in the main sequence, they're going to burn up their fuel a lot faster. So after about 10 million years, all the hydrogen in the core is burned up, fused into helium. Now, hydrogen keeps fusing in the shell around the core, but the core itself has used up all of its hydrogen and turned it into helium. Now, when that happens, the core collapses due to gravity. And when that happens, when the core collapses far enough, then it can start to fuse helium into carbon and oxygen. And then this cycle keeps going until we finally get to a core of iron 56. So carbon and oxygen fuel into heavier elements. Those elements fuse into heavier elements. And finally, we get silicon fusing into iron 56. You can see there's an iron ash core in the middle. What it means by iron ash is that iron is no longer usable as fuel. So the iron can't fuse anymore into creating heavier elements. So we have this basically unusable iron ash core. Now, as we go through these cycles, they start to take less and less time. So the first cycle is about 10 million years. And the final cycle, when we're fusing silicon into iron 56, it only takes a few days for that to happen. And this leads to the conditions that give us a supernova. So at this point, when we have an iron core, the star can no longer be in equilibrium because there's no longer any radiation pressure really pushing out, or not enough anyway. So when this happens, all of the material in the star implodes in on itself, so collapses in on itself. And when this happens, as we know, it creates neutrons. And when we create neutrons by combining electrons with protons, we get lots of neutrinos as well. So we have neutrons and the neutrinos being shot off from the star when it implodes like this. And eventually, this implosion is stopped because of neutron degeneracy pressure. Remember, this stops us from getting a black hole, and we're left with a neutron star here. So we have neutron degeneracy pressure, and that suddenly stops the implosion, and that creates this big shock wave that goes outward from the core. And this shock wave causes more fusion reactions to occur as it passes outward from the core. Remember, these stars are huge, right? So it's going to take some time for that shock wave to go from the center of the star toward outside of the star. So as the shock wave goes out, it causes fusion reactions to happen outside of the core, and this provides enough energy to fuse elements heavier than iron 56. And this lasts for only a few hours. And then the shock wave reaches the edge of the star, and temperatures suddenly rise to 20,000 Kelvin, and that explodes the star and shoots material out into space. And this material is where all our heavy elements come from. So this shock wave creates fusion with iron and other elements. We get our heavier elements, and that is what shoots out into space and can create planets and other objects in the universe. Okay, so finally we're going to talk about how to distinguish these two types of supernovae. So as we can see in this graph here on the right, we have relative luminosity on the y-axis, and we have days after the maximum brightness, or just time, on the x-axis. So we can see here that at their maximum brightness, the type 1a supernova emits light at 10 to the 10 times solar luminosity, and this rapidly reaches a maximum. And then it tails off over around 6 months, pretty smoothly as well. Now, the type 2 supernova emits light a little bit less bright than the type 1a, about 10 to the 9 times solar luminosity. And then the luminosity falls slightly, then plateaus slightly as well for a few days, and then it falls rapidly after it plateaus. So there's a big difference here between how light is emitted in these two supernovae. And this is how astronomers distinguish these two types of supernovae. That's all we have for today. I hope you enjoyed learning about supernovae, and I will see you next time.